So now, before we continue to understand our next unit, that is gamma decay, let us first have a look at the figure on the right side of the slide. This figure shows the beta decay of the 27 cobalt 60 nucleus, which is followed by the emission of two gamma rays from de-excitation of the daughter nucleus 28 nickel 60. Let us look at the figure. The top horizontal line shows the energy level of 27 cobalt 60, where 27 is the atomic number and 60 is the mass number. The cobalt 60 nucleus undergoes a beta minus decay along with the emission of antineutrino, and it gets decayed into the daughter nucleus 28 nickel 60. The 28 nickel 60 is an unstable nucleus. It cannot stay in this state in which it is formed after the decay of the cobalt nucleus. Therefore, this 28 nickel 60 nucleus emits out two gamma rays. First one of 1.17 million electron volt, as can be seen on the slide, and then its energy level reduces. This is followed by the emission of another gamma ray photon whose energy is 1.33 MeV, and then this excited 28 nickel 60 unstable nucleus, after the emission of two gamma rays photons, sequentially comes to the ground state. So in this figure, this lowest horizontal line represents the energy level of the 28 nickel 60 nucleus, which is stable. The one which is above is the excited nucleus, the unstable one, and this horizontal line is that for the cobalt 60 nucleus. Let us now understand gamma decay. When a nucleus in an excited state spontaneously decays to its ground state or to a lower energy state, a photon is emitted. So I give you the example that nickel 60 decays to its ground state or lower energy state by the emission of two photons consecutively. What is the energy of this gamma ray photon? It is equal to the difference in the two energy levels of the nucleus. This is known as the gamma decay. The difference in nuclear energy levels is the order of million electron volt. As you can see, it's 1.17 and 1.33 million electron volt here. The energy, which is a million electron volts units, corresponds to the radiation of extremely short wavelength, which is shorter than the hard X-ray region. Typically, a gamma ray is emitted when alpha or beta decay results in a daughter nucleus in an excited state. So, this is not the only example of the gamma ray decay. One can find several examples of an excited nucleus decaying to its ground state with the emission of the gamma ray photon. And the excited nucleus can be formed because of an alpha decay, a beta decay, or a beta minus decay, or a beta plus decay. I hope the concept of gamma decay is now clear to us. These energy levels shown here are just a diagrammatic representation where the y-axis consists of the energy levels in million electron volts and the x-axis does not have a meaning, so it's just a schematic diagram. It means that the nucleus exists in several states The lowest energy state is called the ground state, and states higher than the ground state are called excited states. This is just like the concept of electrons revolving around the nucleus in various energy levels, as you have known in the case of a hydrogen atom. The details about the levels of the electrons within an atom are explained in the chapter of atoms. And here in this chapter, we have understood that even the nucleus has several energy levels. The lowest energy level is called the ground state, and the excited energy levels have a energy which is higher than the ground state. With this, we come to the end of the concept of radioactivity, the alpha, beta, and the gamma decay.